there's quite a lot of data on the superparamagnetism from this paper. I'll show you, and let me just turn that up because there's some useful things here at high temperatures. So what do I mean by saying that it's a superparamagnet? It means that you measure the susceptibility as a function of frequency. If you measure it very quickly, the molecule is frozen. If you measure it very slowly, the molecule has time to flip, and therefore there's a resonance somewhere in between. And so this is looking at the susceptibility at different frequencies from 100 hertz to 3 kilohertz, and you see there's a peak which shifts as a function of temperature. This is the so-called blocking temperature, and you can plot the blocking temperature as a function of frequency, and if you add to this much higher frequency measurements that you can get from Mossbauer, you can plot this all of the way up here, and this gives you a characteristic frequency, which is some rate times this, and this is, I say, about 10 picoseconds at room temperature, because the activation energy scale is about a little over 300 Kelvin. Now, this by itself is potentially interesting, because what you see is that even as you're getting up to room temperature, the characteristic frequency of this flip is coming on to an interesting time scale in terms of any kind of biological process. This is the kind of time scale on which things actually move. Furthermore, as I mentioned, and it's not quite clear about the microscopics of this, it's also at some point when the temperature gets up to this scale, you'd really expect the antiferromagnetism to go away, and you expect to go from an antiferromagnet to a paramagnet. And in fact, the bulk mineral has a transition somewhere around room temperature. Okay. So the suggestion there then is that what's actually happening here is not that you're doing any mechanical force, but actually you've got an inbuilt refrigerator. Right, so what do I mean by that? Well, there's a thing called the magnetocaloric effect. So this is actually used to build refrigerators, and it takes you around a thermodynamic cycle. And this is drawn for a ferromagnet, but I'll put it up here. So imagine that you applied a magnetic field and aligned all the spins. Then, if you take the field off, and the system was not supposed to be ordered, it was supposed to be disordered, it's going to find its way to a disordered state very quickly, over here, so the spin's disorder. But that's happened very quickly, and because it's happened very quickly, that's an adiabatic transition, and so there's no heat coming in or out, and therefore you have to balance the entropy change with some internal energy change, and the system will get cooler. So you switch off the field, it gets cooler, and now then you leave it to sit there, and of course it'll gradually warm up, it'll absorb some heat, and you'll get back to the operating temperature. And then of course you put the field back on, and you move over here, and the system is now in the disordered state, whereas it should have been ordered in the field. So in this case it must warm up. And then you allow it to come to equilibrium with the environment, and it ejects the heat to a heat sink. And you comes back that way. So this is the way refrigerators work, or most refrigerators work. You know, the garden variety refrigerator, of course, the phase transition is not magnetism, it's liquid to gas. And the field you turn on and off isn't a magnetic field, it's pressure. But nonetheless, the same principle can be used at any phase transition. And that, I think, really was the proposal in this paper. But it's got some few problems, right? So the nice thing about that is if you are able to induce this phase transition, there's actually quite a lot of entropy. Because the entropy now, you know, it's not relying on all of the spins that are actually lined and pointing in the external field direction. It's all the spins in the crystal. The entropy is of order kT times the log of the moment. And this will typically then, in an adiabatic change, result in temperature changes of the nanocrystal, which may easily be tens of Kelvin. This is how these things work. Okay. And furthermore, usually there's particularly for an antiferromagnet, there's always a strong coupling to to elastic effects, and therefore the crystal can change its shape. So going through this, you would also have a shape change. However, in order to do this, it requires a refrigeration cycle. Because, of course, imagine I've got a little nanoparticle in here, I'm applying a field. Yeah, the first time I do it, it cools down. But then if I leave the field on, nothing else changes. I actually have to take the whole thing through a cycle. Okay? So I'll have some kind of cycle like this. And this, of course, would be the temperature change. Heating, cooling. And I will need enough time to equilibrate with the environment, so this has to be long enough. But it's also true that I don't change the average temperature of anything. Right? So you're either absorbing heat from the environment or giving it back to the environment, so you don't change the environment at all. And furthermore, you'd actually need really good contact between the protein and the ferritin. Good. And poor contact with everything else. Because even though I say I may get a temperature change of 10 Kelvin or so associated with this little nanoparticle, it's in a bath, right? And it will very rapidly equilibrate to that, and therefore it needs to be kind of embedded in the molecule so that it's preferentially operating next to that. If I look at magnetoelastic effects, again, thinking about this small molecule, if there's even a few % change in the shape, which you can easily do, that in the end is probably no more than a displacement of about 1/10 of a nanometer, which isn't small, but potentially could work. And of course, there's no evidence for a nearby phase transition in ferritin. Now, so I think one is still confused about what might actually be happening in this system, if indeed there is something there. I sort of begun to be convinced that there is some effect which isn't a placebo effect. I mean, a placebo on the experimentalists rather than anybody else, right? Not the mice. But I will point out, actually, that there are plenty of materials with really giant effects that you could harness. So this is one of my favorite ones. This is actually a manganate material. These things were fashionable about 20 years ago for something which is called colossal magnetoresistance. So this is actually resistivity on a log scale as a function of temperature. And at different magnetic fields. Okay. Now, this happens to be a low temperature one. You can make these things happen near room temperature with very substantial shifts of the transition, and there's a huge amount of entropy here. And also, there are other things that you could find useful, like a metal insulator transition that goes along with it. Okay. It seems to me to be not impossible to imagine that maybe not with ferritin, but maybe with other materials, if you can find a way of making them, biologically, getting them biologically into the body, or you could tune things to make them operate in certain ways. There is potentially, I think, enough magnetic entropy in these materials to have a substantial effect. And that actually is where I wanted to stop. And see if somebody else has got a better idea, by the way, about how this might work. Thanks.
Okay. Questions, comments? Yes, Jose.
If the tunneling effect, how many spins are you flipping?
All of them.
What?
All of them.
And they are what?
Oh, so the 4,000.
4,000.
4,000 spins.
Computer probability.
Well, as I say, again, so the interesting thing is, this is another place I say where theory and experiment don't agree. It seems to me to be a very large number to actually get a decent tunneling rate. But as you know, computing tunneling rates is a serious challenge. But experimentally, it is true that as you go down to low temperatures, below 10 Kelvin or so, then the magnetization certainly continues to fluctuate. It's no longer activated. And there are a few other aspects of it which are...
Effect or some things moving around.
Well, Right. So again, now you can get into details and say, are they all tunneling? Could there be some defects? Could some of them be there? That's been occupying people for a while.
Peter?
I kind of lost a little bit of track through the very fascinating theoretical discussion about what the experiment was. In the sense
sorry.
that I can easily imagine that you can put ferritin-coated genetic particles that go somewhere specific.
Right.
Just because they're foreign, they do something. It seems like the experiment's supposed to tell us that something's different when they're done with a magnetic field on than when the magnetic field is off. That's what I missed.
Right. So actually, on here, so this is regulating glucose, right? That's the right. So if you like, there are many experiments in here, but this is sort of the key one. If you like, you inject somewhere back here. This is one of these curves is with the magnet, one of these curves is without the magnet. Right. So everything else is the same, and you're just measuring the blood glucose level in doing that. But no, there's a few other things.
So something does happen without the without the magnet.
Right. As I said, there's.
So
I mean,
it's kind of an enhancement.
But
that might suggest there's some kind of more macroscopic thing going on, like you turn the magnet on and it just.
Well, I mean, but
go
actually,
through
notice
the
you've
needle
got
or
you've got
something
an
like that.
anesthetized mouse at that point. So you might expect something to happen there. I mean, this one that I showed you, I didn't talk much more about. It's actually a little bit easier to believe in terms of mechanism, is where you actually treat with RF, right? And in this case, again, they've done actually quite a few cell level tests to demonstrate that they can. So these. Sorry, I think I probably must have been on a previous, or maybe I left something off here. Sorry. Right. So these are different cells which have gone through somewhat different protocols for all of this. So this is not a whole mouse. And again, you have to believe that the control is here, the magnet is there, and this is, what is it looking at? Sorry, it's a change of, I think that's actually calcium, which they measured there. But by the way, I mean, there's all kinds of ways that these things can go wrong. I think you know that.
My question is close to the one of Peter. I must have missed something. In your title, it was Magnetogenetics, and blood glucose and other things are exciting and interesting, but doesn't seem to be genetics.
Oh, okay. So the reason that this is genetic is right back here. Is that these things are tagged. Right. So you can choose. So you have a ferritin with a tag, and you can make that genetically specific to bind to different places in the same way that you do with the optogenetic molecule. Right. So take your optogenetic protocol, replace GFP by ferritin. That's the sales pitch. Right. Yeah. Sorry. Well, I didn't say it very clearly, but that's why it gets people's attention, right? So
I have two questions.
Yeah.
I mean, if the goal is to just why not just put a ferromagnetic particle in? Why are you doing it in the case where the effect is going to be smallest, except through the surface effects? And the second question is, what strength RF are you talking about? Are we supposed to go back to worrying about cell phones again?
Oh. Okay. Fine. Right. Okay. So right. So look, obviously the right thing to then you get to birds and seagulls and whatever things like that. Right. So if you wanted to run the numbers for a regular ferromagnet and say how much magnetic moment do I need to have this, I would need a pretty sizable magnetic particle to be able to do this in.
So magnetite, the type you have in bacterial cells, is not going to do anything.
It's not actually going to do anything, right? Okay. So, and then I think for that reason also, as I say, I think that this is still no, RF at the level of cookery rather than our RF at the level of cell phones.
Okay, so we can't